Okay. Yeah, I'm Dr. Manmeer. Yeah, I'll be sharing the slides also. Thanks for reminding. And so I'm sharing the whole screen. I hope that will help me. This is the program that we are going to discuss today. So let me begin with, so I've opened my collaboratory and I've opened this file called Neural Network Wind Energy Python file, right? So you can see here that I'm using a Google Colab notebook here, notebook that I'm using here that has several options here: file, edit, view, insert, runtime, tools. So this is basically an editor. Because we are running it in Jupyter notebook environment, so you will see that each code, there can be two different types of cells. One is a code cell, the other is a text cell. For example, this cell that I click here, I'm clicking here through a mouse, left click. You can see that this is a, sorry. If I click here, you will find that I have written here, first we mount the Google Drive where you have your data and codes. You would like to keep your code here also, and as well as you have the data. So if I just remove these two and go to the next cell, I mean, just click on this, you can see that this will be coming in a small size. But if I again click and put here two hash values, you can see on the right hand side it is showing the size that will be after execution of this cell, that this will be the right hand side that will be visible. Okay, so there are two types of cells. One is a code cell, one is a text cell. Text cell helps us write the comments or more description. And then there's nothing, the next element is a code cell, which is the next cell, which I'm using here. So you can see that in this cell, when I click on this cell, on the left-hand side, there is a button to run this cell. As you know that Python uses interpreter, so you can run each and every cell separately. So from here, what I'm doing is that from Colab, google.colab, I'm importing my drive, right? So I'm actually mounting my drive. Left-hand side, if you can see, files on the drive will be there. The moment I run this by clicking on this, you will find the result of this cell drive already mounted, because I have already mounted. All right, so when you click on here, just see on the leftmost side of folders. So when I click on here, you see that my drive is being shown here. I click on the drive, right? So my drive, it will take some time because my drive is containing a lot of data. So you can see that these are project data, academic talks. This is my Google Drive, it is showing. And there are so many folders there in the Google Drive. In one of the folders, my PhD student, Purnima PhD, first she's doing PhD on some agriculture project. So I click here again. Sorry. I click here. When I expand this, you can see codes here. On codes, when I again expand the codes, when I expand the codes, you can see that here on the left-hand side, this wind turbine data I have. So I will right-click on here, right-click, and I will copy path of this data folder, right? So I will copy path by just clicking here, left-click, and then what I will do, I will now put it off. Then we change the directory to place your data is present. So here you can see I'm using CD with an ampersand sign. CD, so that I remain in this folder. Whatever I do, I will, if I write the code, that will be also living in this folder. So what I will do, that I will, for the sake of understanding that how a cell is added, I will put here, see on the left hand side, plus code. So the moment I write plus code, you see that another cell is created. So when you use plus code, a new cell is created, right? It can be code cell, and when you write plus text, a new cell is created for text. So this is just a demo of a text cell. This is what I'm writing here. And the moment so this is and when I go to this, you can see that this is just a demo of text cell. Now code cell here. So what I'm doing, that I want to change to that directory. So that directory's path that I have copied, I will be pasting here, right? As you can see on this upper cell also, the things that we had already done: content drive, my drive, Purnima PhD thesis classification. This is a drive which is existing in my Google Drive. Codes. In this, we have created, we have our wind turbine data set. So this is what I have executed. So actually I've already executed, so I will be deleting this code. I was making it for you to understand. Please feel free in asking questions if you have. Right. Now you can check whether if your data file is present in this by just using the ls command, which is a simple Linux or Unix command. So this is this exclamation mark ls that I've used. So you can see that here my file, which is a CSV file, is present. The CSV file is containing the data. What kind of data it is containing, we will just see after a little while, in the next few cells. Apart from this, you can see that it is RNN wind energy. So here we have used a recurrent neural network for interpreting and for predicting the wind, for interpreting the data of the wind turbine and predicting the wind energy, right? So there's another file that we have. Okay. So I now I run this cell. I've run this cell, the output comes here. So there are two files in this. One is a data file and the other one is a code file. Okay. Now we import pandas. So how do we import pandas? So just a minute. How we import pandas? Before we go ahead with now we import pandas, you must be thinking what is panda if you are not familiar with Python programming. So let me first go to another slide for those who are new to Python. So Python is a very powerful and fast language, which is, if you see that Python is a programming language that lets you work more quickly and integrate your systems more efficiently. In fact, Python was made for people who were not very efficient in C coding, like they were finding it difficult with pointers and many other data structures types. You have to define each and everything well in advance. So in order to eliminate all these things, to overcome all these things, a scientist only wants to write a simple code so that his program runs and is able to build efficient models. That was the idea, right? So Python was introduced to have a larger family of scientists who can code efficiently without any hassles, right? So we will be doing it in Python. Next thing that I want to show you is that we will be also using Keras library. So it is a Keras IO. This is an environment which gives you Keras gives you a very good environment for coding. It has huge library. One thing which you can see is examples here. It has a lot of examples starting from image classification to 3D image classification for CT scan. There are a lot of code available. If I take any simple code like multi-class semantic segmentation or monocolor depth estimation or image captioning, think of any important machine learning problem, you will see the code is available here. And the codes are very simple codes are there, and people are contributing in writing these codes for the research community. So that is why Keras environment we will be using. I may also be using, although that is not very much required, but Numpy. So Numpy is again a library, and it helps us with numerical computation and scientific computation. It helps us arrange data in a very easy way, and therefore for many computational problems, you can use the library. So you can see that the Numpy offers comprehensive mathematical functions, random numbers, generators, linear algebra routines, Fourier transforms, and much more. It is very fast and versatile. It has it facilitates vectorization in a very simple way. So with these tools that we have in our hand, I go back to our own our original code, that is finding out, given the data of low voltage active power that is being generated from the wind turbine, we have the dimension, we have the attributes, that is wind direction, right? You must be having some attributes to check if these are the attributes of the wind, what power can be generated, right? So there is those wind turbine manufacturers, they give an average theoretical power limits, that this must be the power, this theoretical value is given, and our active power should be quite close to that, depending on the wind direction and the speed that is given to us, right? So the idea is that given the wind speed and the direction, can we build a model that is able to predict what should be the power value, right? So here we will be using Pandas, which is a Python package providing very fast, flexible, and expressive data structure designed to make working with relational and labeled data easy. So it makes things easy for us. You can read further about Pandas from here. So what I'm doing, I would like to import Pandas as PS, right? PD. And so when I write import Pandas as PD, that means whenever in future I will be making use of any Pandas function, I will be making use of PD in place of writing full as Pandas. You need not write here as PD. You simply can write import Pandas, but every time you will have to write full string Pandas, right? So just for easy, for making life easy, we write import Pandas as PD. Now read the data using Pandas library function. So which Pandas library function? This PD stands for Panda. Read CSV file, right? So what I'm doing, that I'm reading the CSV file, which is given to us, t1.csv, and this file is containing the data that I will show you. So it has read the data. Once it has read the data, let us see what kind of data is this. So I run this code. this cell, every cell I'm running one after the other. You can see the data contains date and time. As you can see here, it is a 2018 data, date and time, LV active power in kilowatt. The value is given here, say 380. Wind speed, which is given here in its units. Theoretical power curve, that is kilowatt per hour. So per hour, it should be approximately this. This is what is theoretical power curve giving. But the actual wind, you can see that the LV active power turns out to be this. And the wind direction is also given in degrees, right? So everything has its own unit. So this data head, you must be worrying why I'm using data head, just to see the top 4 data, just to see what kind of labels are there in X, Y, Z, and all those columns. So what we will be doing right now, will be solving a very simple problem that given the wind speed and the wind direction, is it possible to get the value of LV active power, right? So I have got 2 attributes or 2 features, that is wind speed and wind direction. Can we predict the value of active power? Theoretical power curve, we will not be using for the moment, right? So this is the data head. So if I use here, say 7 and run the code, it will show me the 7 top values of the data that is present in our t1.csv file. So this is the format of the data in the CSV file. Now I go to data describe, right? If I go to data describe, my dear friends, you can see that it is giving the entire description of 550,529 entries. After every 10 minutes interval, the data has been recorded of a wind turbine. So all these data have been recorded through a SCADA system. A SCADA system is deployed to check, to monitor if the wind turbine is working well or not. And if there is an anomaly that can be detected, like if suppose this active power and this theoretical power curve, I do not know as an electrical, people in the electrical energy area who are working with control systems for power systems, they may tell better that if anything happens which is very much away from what is expected for the average value, say some 10-15% here and there, if something happens away, something happens different from that, perhaps that can be an anomaly, right? So you will see many papers in this direction of anomaly detection using this wind energy or any other, using this SCADA system data. So this is the SCADA system data, which you can find here. You can check, you can Kaggle, this is given in the Kaggle. When I click on this link, I hope you can see that wind turbine SCADA data set. Can you see my this Kaggle page?
Yes, ma'am. Yes, ma'am.
Yeah, thank you. So wind turbine SCADA data set is data which is given about the data set. In wind turbine, SCADA systems measure and save data like wind speed, direction, generated power, etc. for 10 minutes interval. This file was taken from a wind turbine SCADA system that is working and generating power in Turkey. The data in the files are like date, time, LV active power, wind speed, theoretical power curve, that the turbine generates with the wind speed that is given by the turbine manufacturer. So this is the specified, that finding or using a formula, turbine manufacturer might have calculated it, wind direction, right? And then the data, you can see the details of the data. So the data is given here. You can see this data is given, and the variations in the data is also being shown here, right? And then some people have contributed to code, discussion, metadata, various things are given. So you can get this data from this Kaggle website. So I go to the new, this. So read the data using that we have read, and then we have shown you the header. Data describe can, so this is also a function. This describes the data. It gives you all the frames that are available in the data. So there are total 50,530 samples that are taken. And there are 5 columns, right? Date, time, as I described before. Now we prepare the data for building the neural network model, and I seek your attention here. What we do, right now, I'm going to use only 2 features. There are actually 2 features. One is wind speed, the other is wind energy, wind direction. So the wind speed, the column name here is wind speed. So what I did, I used here input 1 as the array, which will be storing the data of this column, wind speed, right? And similarly, input 2 is will be storing the data corresponding to the column wind direction, right? I mean, you can use a theoretical power curve for some other application. Right now, this is a normal neural network regression model that we are constructing. Suppose you wanted to make use of an autoencoder, then you could have used the theoretical power curve also, right? So then what I will do now, well, any neural network model that you make requires you to normalize the data. Why? Think of, say, 3 different dimensions. One is, say, wind direction. The second is wind speed, wind direction, and second is wind speed. And they have different units. Some feature can be varying between 0 and 1. The other feature will be varying between 1 and 1000. The third feature may vary between 10 and 20. And what will happen? The feature which is varying between 1 and 1000 will be dominating the other features. So for this, what we do is that we normalize all the features and the data, in fact. So what I've done is just simply, in a very simple way, input 1 is equal to input 1 divided by whatever is the maximum of the input 1. Mind you, that this maximum should be away from 0. But we have already seen that this is away from 0. So this is not 0. Therefore, we have divided by this. So once we do it, run this code cell, you can see that there are 50,529 examples, and each one is now normalized by dividing it by maximum of this string. So this is wind speed. The same thing I will be doing, my dear friends, for the second column, that is wind direction. So we have divided by the maximum input 2. So wind direction, length was of this data is 50530, starting from 0 to 500 and 529. Yes, 50530 data, and data type is a float type. Here also you can see that the data type is a float type, right? Before that, also you can see that the data was a float type data. Okay, so now we are preparing the data, right? Now, the second thing that I will be doing, that I will be, so this cell I have made, this commented in this, otherwise you could have used this third input also. If you run this, the third input can be seen, which is the theoretical power curve data, but I have commented this. So I comment this. I don't require at the moment. Now, This is purposely we have done to tell you that how we can make use of NumPy as NP, like how can we make use of NumPy? NumPy provides us writing arrays in a very simple way. So what I've done, import NumPy as NP. X is equal to np.array, input 1. Now see what I've done, input 1 was say wind speed, right? This wind speed had 550,530 columns. Instead of taking all those columns, all those samples, I've taken only 1,000 samples. So what I do, np.array, that means it is an array format in NumPy, array format, where first entry will be input 1, that is wind speed, from 1 to 1,000 samples. And similarly, the second entry will be again 1 to 1,000 samples of the wind direction. Okay. And then, all right. So this again is a commented column, this commented statement, which you need not use. And then we go to X is equal to np dot transpose. Now, why this? Why we need this? Because otherwise, if we don't do it, let me just use it. It is actually giving me 2999, which is not in the format that is desired by the Python function that we will be using. That is available in Keras, in the Keras library, the functions that we will be using to build our model. It is in a different format. And therefore, we will be making use of transpose function. So when the moment I write an X is equal to np dot transpose X, it will be transposing the matrix. And now I can find out the shape of X. Shape of X means dimension of the vector X. So my dear friends, I hope you have understood that X is equal to an array of size 2, where we have 999 entries, 999 entries of wind speed and wind direction. So it is a 2-dimensional array with entries containing wind speed and wind direction. Okay. So we have prepared our data, and remember that we have to also prepare because it is a supervised learning. So we also have to give to our model the corresponding label or values to be predicted, expected values. One is expected value or the desired value. The second will be actual predicted value, right? So these are actual values of the wind power, of the active power. So I consider that as the output data, expected output data. So LV active power in kilowatts, that is the expected power data. I have taken again from 1 to 1,000. Output shape you can see is 999, right? So I think I have, I have also output is equal to output divided by max output, like max output. Then we have divided it by the normalize this data as well. As you can see, we have normalized this data, active power. And then sklearn. Sklearn is a wonderful library where you can find not only a lot of data, synthetic data, some real data, as well as a lot of functions are available in sklearn. It's a scikit library, and you can search it on the Google if you have never used it before. And it has also a lot of codes available. So from sklearn, what we are doing is we are using train test split function. As you can see, this, I've just clicked here. You can see that this function is divides the entire data into two sets. One is splits the data into two sets randomly by checking if you give an 80-20 ratio, it will divide it into 80-20 by shuffling the data, by randomly selecting the data. So you can see on the train test split function has array, test size, train size, random state, shuffle, and stratify none. So you can see that I have imported from the sklearn model selection, I have imported train test split, that I run this code cell. And then the next statement that you can see is, I think we have imported Numpy before, so it was not needed, right? So this is not required. If you import Numpy before, you don't need it because this will already be imported. This is already imported. So now I'm dividing the data. What we are doing is we are dividing the data, train underscore X, test underscore X, train underscore Y, test underscore Y. So अब हम क्या कर रहे हैं यहाँ पे? We are doing training testing data split. So I'm making use of this function train test split function, which we have just imported. np.array X, because X is our data. np.array output, that is our Y data, the label data, the predicted, the actual values of the active power. Test size is equal to 0.1. That means I want test size is equal to 0.1. If it is 90-10, let me take 80-20, right? Here I would like to tell my participants here that if the data size is small, generally we take 70-30 as the train test split. If the data size is of medium size, like 5,000, 6,000 samples, then we generally take 80-20. But if the data size is very large, like we have here 50,000, I do not know whether this is large enough for wind turbine or not. But if it is large, then we can take even more, like 95% train and some 5% test, right? So that is very much possible. So here, once again, I go to this run cell, but I go back to this to show you that what else is possible here, right? Oh, sorry. Yeah. So you can see that train size, we have train size, test size, random state, none. So random state, we have written here some value, right? So there are various things you can go through this, what is what, right? And shuffle is equal to, just a minute. Did I write shuffle here? Shuffle is equal to true. So let me write shuffle is equal to 2. Just a minute. Let me use the correct format. Shuffle is equal to true. True, capital true. Shuffle is equal to true. Am I right? Yeah, fine. So then I run the code. Oh, what is wrong? I did something wrong here. What did I do? Oh, this is comma. Now it's running. Now I find out the train shape. Now the train test, because we have already done this. So the number of training samples will be 799. Number of testing samples will be 200. And the number of train Y, corresponding Y samples will be the same. Y labels will be the same number, and similarly 200. So after you have prepared, there is some question, it seems. Dr. Manviria, come after. Thank you. Yeah. So now you are ready to construct your neural network, right? So now I go from here, TensorFlow, import. So from TensorFlow, I have import Keras, right? Now Keras provides, there are two different types of models that Keras provides here, as you can see from here. So I would suggest you to go through this, like getting started. So here you can see that what kind of models are available. So we will be making use of sequential models here, right? So I go to this. I will be making use of sequential model. So Keras.models, which kind of models? Sequential model that I'm using. So if I use Keras models, so you can see that you have a sequential model. So why sequential model? Because you will be adding one after the other the layers. So we will be using sequential models here. So I have made a model. I'm building my model by first specifying what kind of model I will be using from Keras library. So it's sequential model. Then model.add. Now this will be my first layer. Model.add Keras layers input layer, and shape is equal to 2. Why shape is equal to 2? Because we have 2 columns only, wind speed and wind direction. Now then I will be adding the first hidden layer, which is a dense layer, which consists of all the neurons are connected to all other neurons from the previous layer. That is known as the dense layer. So you have, when you have connections like this, that every neuron is connected to every other neuron, like this is connected, then this is a dense model, or this is also known as fully connected model, right? So that is what I'm using here. There are other types of models also, which you can find in the literature. So like convolutional neural network or recurrent neural network. Then I have added a second layer here. This is the second layer, the third layer, and the fourth layer. So you can see that in the first 3 layers, I have used the activation function as ReLU. And in the fourth layer, I have used the activation function as a sigmoid. Now, in order to understand how have you made your model, what are the trainable parameters, you can see that the layer type, we have all dense layers existing. The output shape coming from this dense layer is of shape 16. Number of parameters which will be those weight parameters that we will be using are 48. Similarly, 272, 272, and 17 in the end, right? 17, why? Because you can see that here you have 16, neurons. So how 17 are coming? Can somebody tell why 17 are coming? Seventeen are coming because if suppose you have 4 neurons at the end, and they are all sent to one final neuron, which is a decision maker neuron. It has its own bias. So it will have its own bias plus the 4 weight parameters, right? So that will be 5 in this case. If there are 16, then it will be 17, right? So that's what. I go back to this. So you can see that these are all total parameters are 609 and trainable parameters are 609. There are models which use the method of transfer learning, where the knowledge of the knowledge of the domain from where some other data has been taken is used to learn or to make new model. So there we call it transfer learning. So suppose you are using a model which freezes these first two layers by the weights, like weights are taken from some other domain, in the sense that the model was earlier trained on some other data sets, right? And suppose these 2 initial layers, we do not randomize those weights, we freeze those weights as the weights which have been learned from the previous model, and then we train on only these two last layers. In that case, you will have only these 2 layers will be having trainable parameters. First 2 layers will not be having any contribution to the trainable parameters. That is why it is written total parameters and trainable parameters. Non-trainable parameters here are 0 because we are starting from scratch. I hope this is clear to everybody. Now I go to optimization that I'm going to use. So optimizer. So Professor Beng was telling about optimization, and they were using different optimization of path optimization, in fact, trajectory optimization, trajectory of the robot optimization. And we also did some work in that direction where we used optimization, but of a different kind for trajectory optimization, right? So there are various types of optimizers. As I told you that we use a steepest descent method. So modified and improved version of steepest descent method is known as Adam optimizer. So here I'm using Adam optimizer. If I load here, you can see that it gives you, the moment you put here, click here, it gives you various parameters that can be set. So Adam optimizer has a lot of parameters. You can see that it has like beta 1 parameter, beta 2 parameter, and epsilon parameter. So many things are there in this Adam optimizer. Here you can also use SGT. If I correctly write, yeah, SGT, the steepest gradient descent. And I run this code. So this code is also run correctly. Now everything is set. You have prepared your data, you have made your model, and now you are ready to train the model. So whatever we wish to, whatever we are training, we would like to train the model on the data that we have, and we would like to store it somewhere, right? So that we can use it later for deployment, right? So we will train the model. Let me run. So you can see here while it is getting trained, you can see that batch size is 8. So instead of giving the entire data at one go, I'm making a batch size of 8, and I'm giving a data of size 888. And I'm using 200 epochs. That means we will be showing the data to the model 200 times. Validation data, that is only test data that we have used here. So you can see that the loss is getting very slowly, the loss is getting down. Loss is what? The difference between the actual value and the predicted value, right? And accuracy, although is stuck at a point, that is just to give you, because we took only 1,000 examples, and we have also not made a real actual, we have not made use of we have not used a very intelligent way of preparing the model, because this is a time series data. So a normal neural network will not actually be of a great use. But this is just to show you how this is happening. So now this is giving the error after 200 epochs. It gave the loss function achieved 0.059. It started with, say, 0.1315, and then 0.0, it goes to 0.059, a little this. Then I evaluate the model on the test data set also. So it is giving me a loss of 0.0553, which is quite close, and accuracy is also close, although accuracy is not good. Then I will be plotting by making use of PyPlot, Matplotlib library. So I will be plotting the data, right? So here we have plot like training loss, accuracy, validation loss, validation accuracy. And then I give the labels also, epoch and this accuracy. You can see that the loss is going down very, in a good way, but accuracy is all showing to be not improving. So how do we improve it? We can improve the model's accuracy by tuning the hyperparameters, by changing the optimizers, by looking at the data, whether the data is providing sufficient variety, or what is the problem with the data. So there can be many different issues why your accuracy is not improving. Here I see that there can be a problem in the data. We've taken a small data set, and secondly, not only a small data set, even if you take the full data set, we realize that this is not giving any better accuracy. So there are what we have not utilized is that it is a temporal data. So we have not utilized the temporal characteristics of the data, and that could be one of the reasons, right? So with this, I would like to stop here, and I will share the code with you. I will share the slides also, yesterday's slides. If you have any questions, you are free to ask me. Thank you for staying here so late in the evening. You know that the professor's lecture was only for approximately 2 hours, 15 minutes, but it was so interesting, and many of you asked questions. It was for around 2 hours, 45 minutes. In spite of that, you gave time and came here. I must thank you all. No questions?